Hi there! Today we will talk about a device that is extremely useful in a hobbyist electronic lab, the multimeter. We will use an unusual format for this channel. In fact, we are going to have a guest that will help me in presenting the topic and will give me a hand in making some experiments to show you the main functionalities of the multimeters. Let's begin! Here we are now. This is Giuseppe, a very old friend of mine, which is today with us to talk about multimeters. I let him introduce himself and then we will move on our subject.
Yeah, I'm Giuseppe. I have the same background in electronics as Carlo, but most of my career has been in development of software for telecommunication. But now I'm getting envious because I saw Carlo's lab, Carlo's electronic home lab, and really it's incredible. And also a follower of his eleneasy program, his eleneasy channel, I should say. Let's try to do something interesting today and let's take a look at multimeters. So I'd like to do my own electronic lab, so I may go into the market to start buying, starting with a multimeter. Let's see what's available today and what are the options.
Let's talk a little bit. Basically, in terms of multimeters, today if you go on the websites usually to buy something like Amazon or other places, you find mostly electronic instruments like this one, for example, which are very useful and easy to use. But in the lab sometimes you need also other kind of instruments like analog instruments. Which usually were very common a long time ago before these kind of instruments became so cheap as of today. And,
so how about this one? I had this one for a long time. I've used it very little.
Yeah, this is a very nice instrument actually. I know this instrument since when I was in high school. It's a very long time ago. But basically this at the time was one of the best instruments of all. And it was kind of costly at the time, if I recall right.
Yeah.
It was difficult to have one of these, for me at least, when I was in the high school. Since
for a student, let's say this was an investment, a significant investment.
Yes.
But anyway, looking at this together today, we were impressed of how many measures it can take, how many electrical quantities it can read. And this is probably 40 years old.
Yeah, I think, it's around 40 years old, this one now. And this kind of things is capable of taking most of the measurements that these instruments can take today. Although this, of course, has much more features because it's digital. The precision, for example, is higher. And also it can do things that those instruments couldn't at the time.
Yeah.
At least they couldn't do it very easily. But for what concerns measuring voltages or currents or even resistors, these instruments are basically kind of equivalent. The main difference for the voltages is actually just the input impedance. For this digital instrument is much higher than in those ones. For those instruments, for example, they were used to measure the impedance in how many ohms per volt they would present to the place where you make the measurements. Basically, when you put the probes on the circuit and the test, you put in parallel to that place and on your circuit the input impedance of the voltmeter. And so, if you have a high impedance, you don't disturb the circuit basically. But if you have a lower impedance, then you may disturb the circuit and even change completely its functionality and ruin the measurement.
And get a false measurement.
Yeah.
So it's important to have high impedance basically on all the instruments that we use, especially we use them as voltmeters.
And I remember when basically there were only analog instruments around. There were these kind of instruments here that were basically the most common used, but they were also around those that were called electronic multimeters, which basically they have just an FET or a MOSFET in front of the input to increase the input impedance. And then everything else was exactly the same as this one.
Yeah.
But just because of that, they costed a lot more of this.
Okay,
They
so
were also bigger.
what are we going to show now? So is it going to be a war between analog and digital, or are we going to say what's best of each
I
one?
don't think so. I think, although most of the time you use this kind of instrument today, sometimes the analog instrument still has its place in the lab because there are some things that these digital instruments don't do very well. For example, when you measure anything you measure, the digital instrument needs to take some time to take samples of the signal under measurement, and so they don't show up the voltage, for example, or the current immediately. And so if you have slow variations of the voltage you're measuring or the current you're measuring or other things like that, this instrument just loses it. It's not able to do the measurements correctly unless it is very fast in doing this sampling. But to have something like this that is very fast, you have to spend hundreds and hundreds of dollars. While if you just need to make an estimate of what's going on and see how the voltage, for example, varies over time with a certain approximation, those instruments that are now very low cost can do that for you, because basically the
movement of the hand will show you pretty much where you are in the scale.
Exactly. So basically the hand will keep moving continuously, but it will show you actually an average of where you are at that moment with the voltage or with the current or whatever it is. This stuff instead, in those cases, unless it's a very costly instruments and very fast in taking the samples, we'll start just flashing numbers totally randomly. Yeah. Because while it's still doing the previous measurement, in the meantime the value has changed already and they don't know anymore.
So it goes up and down and it's hard to make a reading. Well, this one may oscillate a little bit around the value that is going to be the final reading.
Right, exactly.
So it gives you a better idea.
Exactly. So if you don't have so much money to afford a very costly instrument, digital instrument, having both a digital, cheap digital, and one of those analog instruments in your lab, it's actually very effective. So depending on what you do, you can use that one eventually. So should we go and
let's do some examples of some measurements. So what can we measure? What type of electrical quantities we can measure, and how each one of those type of instruments do good with each one of these measures.
Yeah, I guess we can try to do that, and maybe we can do some comparisons and see the difference between the different kind of instruments. Let's go do it.
Let's do some measurement of one of the electrical quantities. Okay, let's go for the voltage. Let's see what each one can do.
Let me get something that we can use for the voltage. I just made this contraption just for this kind of things. Let's see if we can use it for our case. Where do we want to start? Analog or digital?
Let's start with an analog.
Okay, that one?
Yes, let's try this one.
Okay, let's give it a try.
So how much are we going to measure? What voltage?
This is just a regular battery, so should be 1.5 volts or something like that. Maybe you can bring it up to the voltmeter so everybody can see it.
Yeah.
Let's see if,
oh, that's great. So I set it up for a value of up to 2 volts. We should be able to measure up to 2 volts.
That should be good. Go ahead. You can just use one of these.
Oh, that's right. Comes very handy. Okay, so where is the scale that we're looking at? Is it this one, right?
So this is
the black volts, scale over there.
Yeah, it should be the black 2 volts. It should be the last one on the bottom, right? No. This one here,
this
that
one here.
ends with 200, which we have to read as 2. So this means 1.2, right?
1.2, you're right. Yes.
Yep. Yeah, you see, this is the other thing about these old instruments. You have to figure out every time which one is the right scale that you have to use, because it's very easy to make a mistake. And
with the eyesight becoming worse and worse with age, it's hard to figure out which one is the right one.
Right.
Okay.
So, do we want to try now?
Let's try the other digital
one. Which one you want to try? This one or that one?
Let's try this one.
This
looks
one
so.
Here. Okay, let's try that. Let's take these probes here. So this is the other thing. You see the connectors of these probes here, and the connectors of this old instrument, look at that.
Yeah, one
It's
thing
totally different.
to consider, this may be not very conducive anymore. It's been sitting for a long time.
Yes.
Idle.
How long is that you don't use that anymore?
Again, probably I bought it some 40 years ago, and I use it very sporadically. And also I have a digital multimeter at home, so that's the one I use more often.
Of
This
course.
is like, a piece of history sitting in the house.
Yeah. Well, kind of this one too. This is mine, and basically it's kind of the same thing. I just use it very, very rarely, but and then it comes useful in lab. So let's see. This is the common, the input, and we want to use to read voltages, direct current. So it's gonna go right over here. The other thing about this instrument is that you don't have to worry about the range.
Yeah.
Because it takes care of its own, it's auto range. So you just plug it in.
Well, in this one we had to select exactly which part of the schedule we wanted to use, and we had to put the probes in the appropriate position here.
Right, and you have basically to know the approximate range of what you're going to measure. If you don't, then it becomes more difficult because you have to start with the highest ranges
and go down,
and then go down until you make a reasonable measure. So yeah, you see 1.2 volts. That one was measuring quite good actually.
So accurate, they are both accurate, but this one was a lot faster, giving us the read, right?
Well, I don't know if it is fast enough. Let's see. Let's try to have it an idea. So right now it's there. Let's put it in.
It was pretty fast.
Yeah, it was pretty fast. Yes, you're right. Well, at this point we have to say this thing here has an impedance of several megaohms, and so basically is not drawing any current. It's not drawing any current from the battery over here. But this thing here is how much is this? It's 20 kilo ohm per volt. So basically, correct. With a 2 volts range, it basically presents a load of 2 times 20, 40 kilo ohm. So with this one, we were putting 40 kilo ohm in parallel to the battery. And if this was basically, there was already another resistor over here of comparable size, we could have made totally different measurement.
Absolutely.
Just because of that. Actually, you know what? We can try something like this. Let's take a resistor and let's put it in series here. And then let's measure the voltage through the resistor with this one and this one. And let's see what the difference is.
That's very exciting. Let's do it.
Okay. Okay, I got here this 47 kilo ohm resistor, which is a little higher than the
impedance of the analog
voltmeter. So let's see, we should actually, if I'm thinking right, we should read kind of half the value of the voltage with this one, with this resistor, with the analog instrument, while we should read still the same voltage with this one. Let's give it a try. Let's try with the digital first this time. So from here and the resistor now this time. And if I don't hold it very well, it won't do anything. So 1.19 actually. So it went down just a little bit. So it is drawing some current, but very little. Let's see with the other one now.
Look at that. It's about half of what it was before.
Not even
that
measuring
much.
something like 0.5 volts or something like that.
Less than some 0.5.
Wow. Okay. So because of the impedance of this thing, things can go very wrong with this kind of instrument. So whenever you use an analog instrument, you have always to know what you are doing because it's easy otherwise to make mistakes.
Correct. This was very interesting, actually, this experiment.
Yeah. How about we try measuring something else now?
Like resistance, for example?
Yeah, actually we can use exactly this resistor here that I put over there.
How about this box that you made?
Oh, yeah, why not? We can use this one. Does anybody remember this one? This is a resistance substitution box that I built some time ago now, but basically I made a video also on this one. And you can find it on
the eleneasy channel.
Yeah, you can find it on the channel. And actually, right now, the link is coming up right here on the right side of the video. So basically, with this one, we can select the resistors that we want to have at these outputs over here. And we can select anything we want. It's just a matter of selecting the right switches, and everything that we see over here will be added up to the output. So for example, we can put 200, 220 kilo ohm like this.
Okay.
And we can try to make a measurements. Let's start from the digital one right now this time. So I'm gonna select it ohms right now. And of course I don't care about the range because it's auto range. I just need to select it and put the probes over here. And let's see the readings. So,
221.3. 221 kilo ohms, 0.3.
Okay, so we are well within the tolerances of this, yes. Because this thing has a tolerance of 1% for each of the resistors inside. So 220 kilo ohm plus minus 1%, yeah, we are definitely within the tolerances.
Could be 224, 220.
Yeah, let's try the other one now.
Let's try this one. Again, we need to know how much we are measuring, so we're going to select the range of thousands of ohms.
Okay. Let's put this
Let's
over
move it
here.
closer. And let's see what we get. It's at the very beginning of the scale, so it's hard to make a reading.
Let me hold it for you.
Yeah. So yeah, it's about 220. But again, I mean, the reading that we do on the digital is a lot easier to do on this one.
Yes.
Maybe we can select a smaller value. Move this one here.
Let's give it a try. Okay. Like for example, let me switch this back away. So
20 kilo ohms.
20 kilo ohms. Okay. Let's make 23 kilo ohms. How about that? How much are you measuring now?
23 kilo ohms. We are, well, it's hard for me to focus. Maybe you want to take a look yourself, Carl?
Let's see. Yeah, well, it's in between 20 and
25, right? Close to 25, maybe.
Yes.
Right here.
So, yeah, but of course we are still in the higher part of the
And I'm reading from this side, so I'm making an error. I'm supposed to read exactly perpendicular to this one and use the mirror and the meter to make sure that the needle is...
Maybe it's better if we explain this thing to everybody. You see, there is a mirror right here behind the needle. And basically this mirror is there to avoid making parallax errors when doing the readings. Basically, when you look at the instrument, you can watch it from different positions, and depending on where you watch it, if you are not exactly in the front, you can make a mistake and read the wrong thing on the scale here on the display. The mirror helps you avoiding that. Basically, you look at the needle just with one single eye covering the other one, and you look also at the mirror and the reflection of the needle on the mirror. You are exactly perpendicular to the needle, and so you are making the right reading only when you don't see anymore the mirrored image, and you see only the needle because they are on top of each other. Whenever you see the image of the needle on the mirror, it means that you are not exactly perpendicular to it, and so you are making a parallax error when doing the reading. So this needle helps basically avoiding this kind of errors.
In fact, all of them have always the mirror. And
yeah, all the good instruments always have this kind of mirror on the back to avoid this kind of parallax error. Cheap instruments that are basically also low in precision don't even bother putting a mirror because the precision is low enough that even if you make a parallax error, it doesn't change much, basically.
Yeah. Cool. So it seems pretty easy to make a resistance measurements using these instruments.
Yeah.
Right?
How about
capacitance measurements, maybe?
Sure, why not? Let's do the capacitance measurement. For that, the digital instrument, it's the easiest to use in general. You just need to use a little device, which is right over here, basically, that you insert in the right place in in the instrument, and that's just because this way it's easier to insert the capacitor inside these little holes over here rather than using these probes, which on the other hand, with all these long wires, may cause error readings when you measure capacitances or inductances, because they themselves may have parasitic reactances, either capacitive or inductive, and so they may alter the reading. Instead, using this one, we are very close to the instrument, and there is nothing in between. This presents to the instrument known internal capacitance, parasitic capacitance, which is taken care of when doing the measurements. So the measurement is practically perfect.
Can we still use an analog to measure capacitance?
Some analog instruments can do that. This one, let me see if it's possible. This one is not capable of doing it, for example.
This one can, but we need to have an adapter that right now it went missing after 40 years. So basically it uses the power from the line, and they say it can measure capacitance as well. In fact, if you can see this red scale, it reads PF, picofarads. So there is a way to use analog instruments to measure capacitance. But nowadays, I think we can use let's just do some example. I have a box full of capacitors over here, so let's pick a couple of them just to show how this works. Let me pick one right over here, for example. I won't even looking at the value. We just measure it and let's see what happened. To measure the capacitance, we have to go right over here on the symbol of the capacitor. So we do this right now. And then we have to insert the capacitor exactly in the two big holes that are over here, and then we do the reading. We have to give it a little time to adjust, and then we can make the reading. How much it
is
says 0.34 right now.
0.24, and the scale is nanofarad right now. So basically this is 0.34 nanofarad or 340 picofarad.
Yeah.
Yes. Okay.
304 picofarad.
Perfect. And yes, this is exactly what it was. So that's good. And let's try with a bigger one. This one, for example. Let's see what we read.
Something like in the microfarad?
No, well, this is still nanofarad, but in the order of the hundreds. Let's see what the readings is now.
207.5, 206.
Okay. Well, it's quite right.
And it's nanofarad, yes.
It's nanofarad. Yeah, actually what this capacitor was a 220 nominal, 220 nanofarad nominal. But these capacitors have a tolerance of plus minus 20%.
Okay.
So really, if it says nominal 220 nanofarad, really it is between about 200 and 240. And we are reading
206.
206. So
we are within the tolerance.
We are well within the tolerance. Okay. Okay, let's try then with the diodes, you said? Mm-hmm. Okay, I thought I had one over here somewhere. Yeah, here it is. I have two actually.
So what can we do with an analog instruments to verify a diode? What can we measure?
The easiest thing that we can do, basically you use the instrument with the set to measuring ohms, so the resistances, and you measure direct and inverse resistance of the diode. When it's polarized directly, you should see a very low resistance. On the other end, instead you should see a very high resistance. Do you know what kind of resistance you have to select for this one to measure these kind of things?
Probably we can try any of the range, like 10 ohms, maybe?
10 ohms? Yeah, I mean, it becomes then just a matter of how much current flows through the diode. But I think maybe
the instrument has a limitation of the current. I think it's only 60 microamperes.
Oh, when doing this kind of measurements. Okay, so
let's see.
We should go. Maybe we want to...
So this looks like inverse polarization, so no current at all.
Let's put it over here so everybody can see it. There we go.
This is direct polarization, so we have current and we are measuring a resistance basically. If we go the other way around, nothing is moving, meaning it's an inverted polarity, and the diode is not conducing any current.
Okay, so basically this is telling us that
where's the cathode and where's the anode? Basically.
Yeah, it tells us that the diode works fine because
it's not broken.
It's not broken, exactly, because in one direction it's supposed to basically prevent the current to flow, and the other direction instead it should favor it. And also we should know from that, if you are not able to see, for example, the black paint over here that basically highlights the position of the cathode, if you don't see that, you can still use the instrument to figure it out. Basically, the diode will conduce current only when there is a negative voltage on the cathode side. So once you figure that out, you know which one is the cathode.
Put it in the circuit.
The interesting thing is that when you use this kind of instruments, the negative voltage is on the red probe, not the black. So the red probe is used to measure positive voltages, but when using resistances, from here it comes out a negative voltage, and it's from the other one that comes out a positive voltage. So in this case, if you put the red probe on the cathode and the black on the anode, you actually see the resistance, and that's because the red one is the one that has the negative voltage.
Cool. So let's take a look at the digital one.
Okay, so we can pull this out. Actually, we can use this one also for the diodes, because we can use the same holes that we were using for the capacitors to measure also the diodes. And we just need to change here the setting. We have to switch over here, which says ohms, diodes, and other stuff. Maybe here you can see it better. So this one is also measuring diodes. Right now, however, we have to change. We have to select explicitly the diode right now. Right now we are seeing resistances. If I change this and move it over here, right now, now you see the symbol of diode. So now we can measure diodes actually. So to do that, we just pick the diode and we put the cathode on this side and the anode on the other side. We insert it in, and actually the digital instrument will give you the direct voltage of the diode. And so we know exactly that the diode is working. We know also what is the direct voltage, and you see, if we invert the position of the diode, we switch anode with the cathode, the instrument doesn't tell you anything. And that's basically the way to recognize the cathode in this kind of instruments. Either you don't see anything, or you see exactly the value of the direct current.
So interesting to notice that we are measuring a voltage here with the digital instruments, while we were measuring ohm on the analog instruments.
Exactly. The analog instrument, the most they can do is just measure the resistance of the diode in one direction and the other. But the digital instruments can do much more than that and can show you exactly the direct voltage. Okay, so basically, I guess this is all I have on this kind of instruments. Do you have any specific thing that you want to add, or maybe your questions? I don't know.
We're going to talk about ranges.
Sure, why not? Well, first thing, we already said that the digital instruments, most of the new ones at least, have a feature of auto range. Basically, you don't care about setting up the range specifically on the dial here. You just select the kind of measurements you want to do: voltage, current, resistance, and so forth. And then the instrument takes care of itself in selecting the correct range for making the measurements. For these other instruments instead, you have to do it manually. Basically, in this case, for example, you have to put your probes in the right places, in the right connector. And for this one, you have to do the right selection with the dial that is over here. But there is one other thing in terms of more than the range, about precision also. Some instruments have a better precision than others. and some of them can measure much lower than others. For example, an instrument like this, you cannot, can you measure microamps with this instrument?
I think so.
Probably you should be
Yes.
able to do that, right?
I think
And
so.
this one is able to do that also. But for example, this one, which is still a digital instrument, cannot do microamps.
It's more probably a field instrument, right? As you were
Yeah,
saying
this
before.
is something that is used mostly for people who works mostly on electric installations to measure high voltages.
Electricians,
and
for
currents and so forth.
example.
Yeah, electricians will be the right thing. This kind of instrument, instead, it can read microamps, and it can go very low on that. It can read the single microamp, actually. And this instrument is basically optimized for work in the labs. Of course, this kind of instruments cost more than this one, and also have, besides the range, have also greater precision than these other instruments. And these instruments, as you can see, they already measure microamps, but these actually are lab instruments. These are not, you see, you can go by today in places where they sell building materials. They also sell this kind of digital instruments, or some simple and cheap analog instruments. But again, they don't have the same range as the lab instruments, and they don't have the same precisions because it's not required for those kind of jobs. But in the lab, where you have to work with transistors, base currents on the order of the microamps or lower,
Like for a Fermi project, for example, right?
yeah, well, yes. You need a sophisticated instruments than the ones used for constructions, and so you have to spend a little bit more, of course, but not that much sometimes. These instruments, for example, though it's has a very good range for use in the lab, and though it has a very high precision, does not cost really that much.
Let's give us a figure. How much would it cost? $100 maybe?
I think it's below $100. I don't remember exactly. And you know what? I bought this on Amazon. Actually, I'm going to put a link down in the description of this video, so you can eventually go take a look. And if you like it, you can buy it. I think it's very cheap for this kind of class of instruments.
What's left, Carlo? What do you want to show?
I don't know. I don't know anything else. So maybe we can. One last thing we could do, if you like, we can measure some currents.
That would be cool. I would like to see this one in action, measuring a current, a small current, maybe.
Maybe a small current. Okay, we can do that. Certainly, we have to do some rearrangement here to put the power supply and maybe a load.
Yep.
The load, we can use an electronic load like the one that I built recently, and for which there is also a video. Again, link over here. You can watch it.
So for measuring a current, we need to put this one in series with the circuit that where we want to measure
Yes,
the current, right?
exactly.
So we have to open the circuit and put this one in series.
Right, exactly. Because I mean, the voltage is something you do it, measuring in parallel to the place where you want to take the measurements. For the current, in order to measure the current flowing somewhere, you have to be within the circuit.
Open that circuit and put
Right.
the instrument in series.
Yes, because otherwise there is nothing that you can measure about. Well, again, there are exceptions. There are some kind of probes, special ones. I don't know if you ever saw those clamps that basically you can attach to an instrument like that. The clamp basically, instead of being in series with the circuit, it just goes around the wire where you're going to measure the current, and it's going to sense the current going through it by induction. Basically, the current flowing through the wire produces a magnetic field around it, and these kind of clamps are going to read the magnetic field. So basically, they will make an indirect measure of the current, not a direct one. The only way to make a direct measure is just to go in series with the wire.
And again, assuming that the instrument doesn't add anything to the circuit, right? It doesn't add any additional impedance or an additional resistance, right?
Right, exactly.
We don't want to disturb the circuit in its
Yes,
own
that is correct. And actually, while this instrument presents a very high impedance for what concerns measuring voltages, For the current, it's just the opposite. They have a very, very low impedance of the tenths of an ohm.
Ah.
And I guess these ones too, probably. It's easy to find internal resistance of about 0.1 ohms or something like that when measuring currents. In both kind of custom instruments, both the digital and analog ones. But again, the difference then it becomes the easiness for reading it. Reading just some digits over here, or trying to interpret the needle here in the multiple scales. So
and it's important if you do hundreds of measurements during your work day or your hobby day, right? I mean, at the end of the day, you are a lot more tired having to read the analog instrument rather than the digital one.
Yes, so this one is much simpler to use, definitely.
Okay, let's go.
Okay, let's do the setup and then we get back to you. So for this one, I will let Giuseppe drive, and he will explain you what we have set up and how does it work.
Okay, so we have the power supply here, which is supplying about 5 volts of voltage. This is the load, which is the variable load that you put together some time ago. And as you can see, if we follow the current flow, we said before that the multimeter is to put in series with the circuit. So that if you follow the flow of the current, from the positive we go in the load, and from the load we go inside the multimeter and back to the power supply. So what we're going to do now, we are going to turn on this, and we're going to set it for amps. You want to start with the amps or milliamps?
Yeah, amps is fine for now, and then eventually you can...
So we turn on the load. Right now the load is not doing anything, it's 0. So we increase gradually until we get the measurements of about 120 milliamps from the meter inside the load, and the multimeter is actually measuring 170 milliamps.
Yeah, we have to note, I already said this at the time when I built that electronic load. The instrument of the electronic load is not very precise.
Not as precise.
It's just exactly the multimeter is much more precise than that. So there is a little discordance between the two, but that's because of the precision.
And we can go up, and you can see that the load increases. And that's pretty much it. So this is a series insertion of the multimeter to measure currents.
How about we reduce the current now? We try. Let's see if we can get in around the milliamps, and so we can measure with greater precision on the multimeter one.
Okay.
So you can. Let's see.
So right now we are set to milliamps.
Yeah, see, that's what I wanted to see. You see that now the multimeter is already measuring something, but the other ammeter is not capable of doing that because it doesn't have the right sensitivity. So how much are we measuring right now over there?
20 milliamps.
20 milliamps.
We can go then lower. You want to try to get to the microamps?
Sure. For that, you have to change the probe, the connection. There is a special connection for the microamps on the multimeter over there. There is another port to use.
Oh, I see this.
Yeah.
It's now measuring 73.6.
This is milliamps or microamps?
Micro.
Oh, microamps. And of course the other meter doesn't show anything at all because
Let's see how
it's
low
not capable of
this
doing.
This is the minimum.
That's the minimum for the load?
For the load, yes.
Oh, okay.
You can only increase from there. But it's pretty good. 73 microamps.
Yeah, actually, if you think about it, I mean, this is the kind of currents that we measure sometimes on the base of the transistors or other devices like that, and
being able to measure
they
that
are very low current, and being able to measure them, it's useful sometimes.
Okay,
I guess we're done with that.
It was fun, Carlo. It was a very fun experience, and again, I love to see your lab, which you have done in your electronic lab.
Cool. That's fine. So, thank you for joining in
was my pleasure.
this session. And to the next time, hopefully.
To the next one.
Okay. Bye, guys. And this concludes our talk on multimeters. I hope you enjoyed this presentation format and that you had an easier understanding of the concepts we presented. Please let us know in the comments your opinion and whether you would like to see this format again for future topics. I have also added to the video description below an affiliated link to buy the digital multimeter presented in the video, in case you are thinking of buying one. Buying the device through this link will help the channel at no cost to you. And you can also help by making a periodic contribution through Patreon or a single contribution through PayPal. Both links are also in the description. And don't forget to subscribe if you haven't done so already, so you will be notified when new videos come out. See you soon in the next video, and happy experiments!